live on YouTube, and we can start. All right, I think we are live and ready to go. Welcome everyone to Radiation Belts in Space Physics seminar. Today we have two outstanding speakers joining us from Berkeley. This is Solène Lejosne, who is going to be the first speaker, and from snowy Los Alamos, Greg Cunningham is dialing in. They both are going to give us talks on their very recent papers on one of the oldest subjects in radiation belts, which is different aspects of diffusion physics and how it works, and how we model it, various aspects, and understand the properties of particle dynamics. We will run it the usual way. We will first give our speakers chance to present, and then we will open it up for questions and comments. Of course, feel free to utilize the chat mode as we go. And with that, with no further ado, Solène, the floor is yours.
Okay, thank you, Sasha, for the introduction. And hello, everybody. So, let me share screen properly. Okay, I hope you can see my screen.
Yes, we can. We're good.
Great, thank you so much. So I'm going to talk about large-scale transport in the radiation belts. And first, I'd like to thank Sam Walton for helping me have some nice illustrations to show you. That's one example here on the right, and we'll see a video on that afterwards. So to begin with, let's start with the current context. And I'll start with also an overview of my talk with this first slide. So the current paradigm to model the effect of radial transport in the radiation belts is through the use of the radial diffusion equation. And this equation actually relies on several assumptions, but one of the strong assumptions there is that the phase space density is independent on magnetic local time. And the reasoning behind that is that even if you have a perturbation that's going to depend on magnetic local time, so what is called also like drift phase structures in phase space density, then this perturbation is expected to dissipate very rapidly. And this is thanks to a process that we call the phase mixing, and that occurs also at the drift scale. So these perturbations, they are not expected to live long, and as a consequence, they are not expected to impact really the dynamics of the radiation belts and their intensity. That said, you know, with the latest missions and instruments that have high energy resolutions, we have many observations of what we call non-diffusive radial transport events that occur in the radiation belts. And these drift phase structures, they indicate that the radiation belts actually, they are at the drift scale, they are not in a state that is phase mixed, but they are in the process of phase mixing. So that means there is always a bit of dependence in magnetic local time. And so from the theoretical point, how important is this dependence? And, you know, the fact that we observe a lot of drift phase structures, does it mean that it happens often, or it takes a lot of time to phase mix? So once the drift structures are there, they last for a long time, or these two effects combine? And also, what can be done when the phase space density depends on magnetic local time? And the long-term question, the overall scientific question there is, how does this feature, this magnetic local time dependence, this non-diffusive radial transport, events, how do they affect the overall radiation belt intensity? And right now in our model, this is not taken into account. The key takeaway messages that I will try to convey with this talk, there are three of them. First is that the phase mixing is usually introduced as an instrumental effect. It's due to the finite energy resolution of the instrument. But it also occurs naturally. So if we had a perfect instrument with, or impossible instrument with 0 of energy resolution, very, very so small, we would still see phase mixing, and it would take way more time than what we expect actually, or what we can see. When we have a dependence in magnetic local time, so the radial diffusion paradigm, it does not hold, but we have another master equation, we have another way to model the effect of transport on radiation belt intensity with the use of a 2D equation. And then we can use this equation as a tool to determine how different the dynamics of the radiation belts they would be if the transport is different from what is modeled by the radial diffusion paradigm. Okay, so this is the current context, right? That was one of the first models for radial transport dynamics. Actually, that shows that radial transport is really central to the modeling of the radiation belt. So you have one of the first equations that were used for the dynamics of the radiation belt. You have the phase space density, is time variation, is a function of two factors. On the left, the radial diffusion equation, and then on the right, a term that models some losses. So what this equation means is that overall, the radiation belt dynamics as a first approximation is mostly some adiabatic effects. So that would conserve the phase space density, to which we add some small perturbation in the third adiabatic invariant. And this small perturbation, we characterize them with the radial diffusion equation. So no injection, no drift structures, this radial diffusion equation, and then some losses. And with this simple equation, there were some good first approximation. There were some works at the beginning of 2000 that showed that it did a decent job at modeling the dynamics of the radiation belts. And one of the limitations of this equation is the fact that the radial diffusion equation is going to behave so as to always smooth the radial gradient in phase space density. That's what you see on the right plot. And so when we see a growing peak in the phase space density, that cannot be taken into account by this equation. So we had also some notable discrepancies when we compared model and data. And these discrepancies, they led to two different types of efforts. On one end, they both indicate that there is something missing in this model. And so the first, one of the ideas was some processes are missing, and we are missing the local wave particle interaction, the role played by chorus. And when we introduce this role, well, we can model a growing peak in phase space density. So, it was indicative that something else was missing in the physics of radiation belt. But in parallel, there were also some works that question the validity of the radial diffusion paradigm as a tool to model the effects of radial transport on radiation belt dynamics. So I note several works there, and what I want to show, so the works, they go from the 90s to a work published last week by Adnan Osman. So it's really a topic that is not new. The questioning of the radial diffusion paradigm is more than 30 years old. And on the right, you have an example of comparison between results from test particle simulation and the solution of the radial diffusion equation. And you see some significant discrepancies. So this current paradigm for the transport is limited. Now, million-dollar question is, what can we do about that? And that's a difficult problem. One of the interesting thing to me behind this equation, right? So when you want to go from Fokker-Planck to the radial diffusion equation, you need to relate two coefficients. You need to assume a relationship between the two of them. And in order to do that, you need to assume that your phase space density is homogeneous in magnetic local time. So there is no magnetic local time. There is the radiation belts are phase mixed. And so there is not so much information on phase mixing that I could find at the drift scale. It is said that it is fast, but how fast is that? It's not clear. So I want to take a few minutes in this talk to focus on phase mixing at the drift scale. And explain a bit about that, because it was first introduced to me as an instrumental effect. So you always, with your instrument, if you think you're measuring 200 keV, actually you have a finite energy resolution. So you're going to measure particles that are between 180 and 220 keV. So you have a small margin there, a small uncertainty in kinetic energy. And because your drift frequency, it depends on kinetic energy, your particles are not going to drift at the same speed. So it's going to be like runners on the track. They're going to, even if they start all at the same time or all at the same magnetic local time, your particles, you inject particles, then if you let them drift, at some point, they're going to occupy all the track because they don't drift at or run at the same speed. Okay, so I have a movie to explain that, and I put also a definition for drift phase mixing. So that's a process by which trapped particles that are initially located at a localized magnetic local time, they end up covering all magnetic local times uniformly at some point. So let's see the movie. On the left, so you have a drift path, you have the Earth in the middle, and the circle is a drift path. The red circle is a sensor. So we're gonna somehow stay there at free Earth radii at midnight or whatever magnetic local time. And then here I put 30,000 particles. They are all at the same initial time, initial place, but they have kinetic energies that are 250 keV with a 20% energy resolution around that. So they don't all have the same energy. And we're going to see them drift with time. So it's going to go fast. So they start, and you see already they all started from the same place, but after 45 minutes, they are already scattered, occupying a big region in magnetic local time. As we're going to drift back through the sensor, right now the sensor, if you look on the right, is not counting any particle. Nobody is there yet, but they're going to arrive. They're going to be seen by the sensor, but not all of them anymore. And as it keeps drifting, the sensor is measuring a number of particles that is becoming more and more uniform. So even if you have somehow an injection that is very localized in magnetic local time, as the particles are drifting, this signal is dissipating and becoming flat. So then you can assume somehow your distribution is independent in magnetic local time. But in that example, you can do that only after about 10 hours. For the first 10 hours, you still have a dependence in magnetic local time in your phase space density. So that's an instrumental effect. And that led me to wonder somehow, if I increase my resolution, so then rather than having 20% of error in the finite energy, I have 10%. Then this signal is going to take more and more time to dissipate. I'm going to see it well longer and longer. So if I had the perfect instrument that measured 250 keV with no error, would this signal last forever? And that kind of seems weird. So actually in space, you have also some field perturbations that are always there, that's going to drive some radial motion, some radial diffusion. So this is going to also influence your drift frequency, because your drift frequency is a function of radial distance. So this is another natural process that's superimposed to this observational process, and that is leading to phase mixing. So if we have better instruments, we see these drift echoes better and better. The magnitude of them is longer and longer, but we have a natural limit that is the phase mixing that is natural and that is set by the field perturbation. So on the right, I kind of want to spend 2 minutes discussing this plot. This is somehow the same thing that I showed you before, but I superimpose some field perturbation in the background. And so if we had a perfect instrument, you see the dissipation of the magnetic local time dependence. It's in blue, and it's taking a lot of time. After 16 hours, it's still not dissipated. It's still not, we still have a magnetic local time dependence. Whereas with a finite energy resolution for the instrument, the dissipation is faster, so that's in red. And you see that we reach a homogeneous distribution function after about 10 hours. So what that means is that when we look at observation of phase structures, if we want to study the amplitude of this fluctuation, actually it is a function of the instrument you're using to look at the dynamics of the particles. So there is a bias there due to the instrumental resolution, and it's also not the same amplitude that was set initially. So we are somehow, when we are observing a drift phase structure, we are always underestimating the natural magnitude of this drift phase structure and also the initial magnitude of this drift phase structure. So its role, it's, the dissipation, they might be bigger than we think, and they might last longer than we think. So it's, it might play a role. Now, what do we do when we have this magnetic local time dependence? How do we take that into account in our model? Oh, no, sorry, I forgot. Okay, so I had one more slide on that. So I somehow characterize if here for the blue, we can characterize the time it takes for this phase space structure, G phase structure to dissipate, and it is as a function of energy and the L value, and you see that it takes time that is hours. So when your fields are pretty quiet, so I use Kp as an indicator of perturbation of the magnitude of radial diffusion. When it's 0, really it is going to take forever for your drift echoes to dissipate. But if your field is, even Kp6, you still are in the time scale of hours. So it takes time for drift phase mixing to occur naturally. So what do we, oh, okay. I want to jump. Okay, so as a result of all this, with higher energy resolution instruments, we have noticed a lot of drift period structures. On the right here is an example at L equal 1.9. So you had the Van Allen probe, they cross the same L value at the same time, but two different magnetic local times, two opposite magnetic local times. You see the fluxes there. on average, if you look, the shape is about the same, but you have differences. So you have observed variations of magnetic local time. So these drift phase structures, they've been observed across energy ranges, in the Earth radiation belts, in radiation belts at other planets, in particular Saturn. They are, interpreted in several ways, but they are there and observed. So what can we do when this is observed? How can we take them into account in our models? So there is actually a work that was published in 1967, and that somehow went unnoticed. And it actually starts like the same derivation for radial diffusion equation, so a Fokker-Planck equation, but without the drift averaging, without the assumption that your phase space density is independent in magnetic local time. So that is at with higher resolution at the time scale of a few bounce periods. And in that case, the master equation to describe the effect of radial transport on radiation belt intensity, it is greater, it is a bit longer than the radial diffusion equation. You see a term, the third term on the right, that looks a bit like the radial diffusion equation, but this parameter, the L Euler, L double stroke, I like to call it, it's not L star, so that is not exactly that. I won't go into details there, but what is interesting to see is that you have terms, the first two terms, they correspond to the bulk motion of your plasma, and then to that you add some diffusive effect in both radial and azimuthal direction and cross terms as well. So we can use this equation to test the difference with the radial diffusion equation when we have magnetic local time dependencies. And somehow to summarize a bit the problem, so on the left, you have this equation that is a bit more sophisticated, but if you assume that your distribution function, this big F, it does not depend on magnetic local time, then this equation, it says exactly the same thing as the radial diffusion equation. So that's going to be on the right. The bar that I put on the F, it means magnetic local time average. So then I can always somehow mathematically decompose my distribution function into a distribution that is the average of the whole magnetic local time. So F bar that does not depend on magnetic local time, and the F tilde, that's going to be the difference between the two, that is going to characterize how the distribution function depends with magnetic local time. And somehow the mathematical question behind this science question is, can the dynamics of my F tilde function influence the dynamics of the F bar function? And so far, we have assumed that this F tilde dynamics, they exist, but they are not going to influence the F bar. So all the drift phase structures, they exist, but their significance is not as important in comparison with the radial diffusion equation, so the dynamics of F bar. So I am working with a colleague on that, Daniel Ratliff from Birmingham University, and so his work is not ready yet for prime time, but we have reasons to believe that this F tilde is actually gonna influence the F bar. Okay, so here is a movie where we implemented this drift diffusion equation in a simple case. It's a visualization of a 24-hour interval. So first, we have some kind of fake injection at midnight, and we're gonna let that evolve with drift and diffusion behaviors. So you see how it's drifting, and you see how the drift velocity depends on the radial distance. So that becomes a spiral, the injection. And then as it's drifting, we have also some diffusion. So the magnetic local time dependence is disappearing. And now after about only 15 hours only, we don't depend on magnetic local time. So now we are in a purely diffusive regime. So we observe the transition from injection to diffusion. We can implement this continuum, and that is interesting in my opinion. Okay, so this is the summary of the points I made during this talk. We have right now the way to model the radial transport. It is radial diffusion, and it's far from perfect. That said, radial transport, the effect of radial transport on radiation belt dynamics, it is a central effect to account for. Radial diffusion, it relies on the assumption that the phase space density is independent on magnetic local time. And so far, the thinking behind that is that any magnetic local time dependent structure is going to dissipate rapidly, and as a consequence, not affect the dynamics of the MLT average phase space density. And whether or not this is the case is still to be determined. We have many observations of drift phase structures in the radiation belts, and that's contributed to a renewed interest in these non-diffusive radial transport processes. The overall role of these processes on radiation belt dynamics is still to be determined, but we have a tool that has been there for a while actually, but that I wanted to highlight, that allow us to carry on with a systematic way to test the influence of these non-diffusive radial transport processes. So that's it for my presentation. I'm happy there is a renewed interest in this, and I'd like to thank also all the colleagues that have been discussed this. I could discuss this topic with, and that are also carrying research efforts in that direction. It's nice to have some energy around this topic. So thank you very much, and I guess I'll stop talking now.
Thank you, Solène. Excellent talk. We have one question in the chat. We can either get to it after Craig's talk, or you can comment on it in the chat, however you would like to. And I think I am going to drive slides for Craig, who had some technical difficulties this morning. Let me go to his presentation and go to presentation mode. Can you all see that in the normal presentation mode?
Yep, looks good.
All right, then the floor is all yours, Craig. Please take it away.
Okay, hello. Today I'm going to talk about a few problems concerning our community's application of the quasi-linear theory to model populations of trapped charged particles in the heliosphere. Thanks to Jean-Francois for inviting Solène and I to give you some theoretical talks today, and Sasha for organizing the session. I've got slide numbers in the lower right corner, so if you have any question, please write down the number. I've also got my email address at the bottom of each slide, so that if you want to follow up with email, you can do that too. Next slide, please. So this presentation summarizes some of the key findings of a paper that was just published in JGR with the same title. The presentation will first provide some context for the paper that discusses why we need to be able to compute so-called local diffusion coefficients. The standard reference for computing these is Glauert and Horn's 2005 paper, as well as J. Albert's paper in the same year. But these papers rely heavily on a series of papers that were generated in the 1960s and 70s. I'll provide a high-level overview of how Kennel and Engelman in their 1966 paper derived quasi-linear theory. My focus here is to help you understand the implications of the Fourier representation used by those authors, which actually may not be general enough to handle, for example, EMIC waves, where more than one frequency can be associated with the same wave vector. There's also a notational problem in Kennel and Engelmann concerning what we call spurious phase terms. The final technical section of the talk, and really the reason I think the paper should be carefully reviewed by those in the field who are doing modeling, will discuss a transformation of variables that Larry Lyons and his co-authors used on a paper that Larry was first author on as a grad student in 1971. That paper uses a transformation of variables so that the Kennel and Engelmann work can be adapted to the situation when one knows the wave power is a function of frequency and wave normal angle rather than the wave vector. The paper shows that this transformation was used incorrectly and that the correct use can produce local diffusion coefficients that are different by orders of magnitude in some situations. This problem is inherited by the 2005 papers and by the more than 500 citations to these later works. So finally, I'll summarize and draw some conclusions. Next slide, please. So as we all know, the Van Allen probes was a huge success, delivering many years of data that sampled a variety of waves and particle populations over a broad range of frequencies and energies. The comprehensive high-resolution data challenges numerical models to explain what's going on. One approach is to use a Fokker-Planck equation, shown here, to model the effect of small amplitude waves on the particle population using diffusion coefficients that redistribute the particle distribution in equatorial pitch angle, alpha, and momentum, p. The diffusion coefficients in this equation are necessarily bounce and drift averages of local diffusion coefficients that would be applicable at each point along the field line in an individual particle's trajectory. An example of solving this equation using wave data from the Van Allen probes and using particle data from Van Allen probes to initialize the calculation and provide boundary conditions is on the right. This was the first storm seen by Van Allen probes just a few months after launch, and it resulted in a number of important papers being published, including one first authored by Wei Chao Tu while she was a postdoc at Lanel. Wei Chao simulated the phase space density of electrons using radial diffusion only, using radial diffusion plus scattering by VLF waves, and using radial diffusion plus wave scattering, as well as a realistic low energy boundary condition for the seed electrons. You can see that the simulation does a reasonable job of predicting the dropout due to outward transport and loss through the magnetopause, and then rapid acceleration of ME electrons later. But there are a lot of knobs when doing calculations like this, so we may have gotten a little lucky. Slide, please. So the standard reference that people turn to nowadays for calculating local diffusion coefficients are the 2005 papers from Glauert and Horn and Albert. These two papers have been cited more than 500 times and are used at the heart of many independent modeling tools that have been developed over the years, including the code I just showed you results from Dream 3D, but also VERB, SteerB, the full diffusion code, the radiation belt environment model, and SLOMBO. These codes have been used to do hundreds of studies modeling the effects of a wide variety of waves like chorus, hiss, EMIC, ECH, magnetosonic, Z-mode, lightning-generated whistlers, and ground-based transmitters. The effects of the waves on the particles has been investigated for electrons ranging in energy from tens of eV to many MeV for Earth-based applications and up to hundreds of MeV for radiation belts around Saturn and Jupiter. You can think of these codes as the leaves sprouting up from the branches of a tree and the 2005 papers at the top of the trunk of the tree. Next slide, please. However, much of the groundbreaking work in this area was actually done much earlier in the 60s and 70s, not too long after the start of the space age. If we look at the bottom of the trunk, we have Kennel and Engelmann's 1966 paper, which is really a tour de force publication that took me months and months of struggling during the pandemic to understand. This paper has been cited about 1,000 times, a testament to its extraordinary contribution to the field and staying power. Kennel and Engelmann started with a homogeneous box inside of which the cold plasma was assumed to have constant properties, and the magnetic field was constant and aligned with the z-axis. The waves were assumed to be low amplitude, and the electric field was represented using a Fourier integral plane waves, each associated with a 3D Cartesian wave vector and a frequency obtained via the cold plasma dispersion relation. The particle distribution was assumed to be independent of the position within the box, but could evolve in time as a function of the non-relativistic velocity components. Shortly after this paper was published, Lurch generalized the approach to relativistic particles for astrophysical plasmas. And in 1971, Lyons wrote a paper that had two significant contributions inherited by the later papers. The first was to recognize that the dispersion relation constrains the components of the electric field with respect to one another, so that there is really only one degree of freedom. And this degree of freedom can just as easily be represented by the total wave magnetic field intensity as it can using the total electric field intensity using Faraday's equation. And so in Lyons' paper, we talk about bk squared instead of the three components of the electric field vector at each Fourier component. The second contribution in that paper was to specify the wave power as a function of the frequency and tangent to the wave normal angle instead of the three components of the wave vector. The azimuthal component of the wave vector is irrelevant since this is the direction of gyrophase motion and doesn't affect the result. In later papers, Larry derived the bounce averaging formula in order to make use of the local diffusion coefficients, and finally generalized the approach by allowing the wave normal angle distribution to depend on frequency so that arbitrary distributions of wave power could be specified. The 2005 papers by Glauert, Horn, and Albert used the full cold plasma dispersion relation instead of the simplified dispersion relation that Larry used in the early 70s. To represent the wave electric field vector via the magnetic field intensity. Next slide, please. So the building block of quasi-linear theory is a representation of an arbitrary wave field using a Fourier integral of plane waves. In Kendall and Engelmann, Cartesian coordinates are used in the Fourier integral, and so the wave vector is expressed using kx, ky, kz as in the figure. Cylindrical coordinates are used to simplify the algebra, and so k perp, k parallel, and k and psi are introduced, where again psi is the azimuthal angle and indicates where the wave propagates in the gyrophase direction. The Fourier coefficients are complex valued vectors. That is, for each coefficient for a given 3D wave vector, k, those coefficients have three components in x, y, and z. Under the symmetry condition assumed by Kendall and Engelmann, it is straightforward to write the sum of each pair of plane waves, one at positive k and one at negative k, as a pair of waves, one of which is right-hand circularly polarized, indicated by the plus sign leading the sine function, and one which is left-hand circularly polarized, indicated by the minus sign applied to the sine function. Because the amplitudes of the left and right-hand waves can be different, any polarization of the combined wave can be realized that's circular, elliptical, or linear. Next slide, please. So the easiest way for me to get a physical feel for what a Fourier integral means is to start with a Fourier series. Imagine a finite-sized box in which the problem is solved. The box has width L, and a Fourier series can be defined that allows wave numbers in each direction to be any integral multiple of the smallest wave number that puts exactly one wavelength in the box, making the representation periodic with period equal to the box dimension. Thus, on a grid in kx, ky, kz space, there is a single complex valued vector amplitude for the Fourier component at each location in the grid. That is, at each intersection of the grid lines I've drawn here, but extended to 3D. Each of these vectors can be understood to represent the wave power in a volume of wave vector space, where the volume is the cube of 2 times pi divided by L. As the box size goes to infinity, that volume goes to 0, and the squared magnitude of the electric field vector as a function of k becomes a distribution function. That is, ek squared is a distribution of the wave power with respect to the 3D k vector, and multiplying it by dkx, dky, dkz produces the wave power in an infinitesimally small volume centered at kx, ky, kz. This understanding of the distributional nature of ek squared is critical to understanding the mistake that was made in the 1970s. A quick note here, the pink box highlights a limitation of the derivation in Kendall and Engelmann that I was able to pinpoint after many back and forth discussions with the reviewers of the paper. Note that in this formulation, the frequency is assumed to be a single valued function of the 3D wave vector k. This would seem to imply that each 3D wave vector can be associated with only one frequency. While this may be the case for chorus, it's not necessarily the case for emic waves, where there are singularities at the ion gyro frequencies that are relatively close to one another. Appendix A of the paper has some implications of this if you're interested. Next slide, please. So the Fourier series that is used to represent the wave electric field can also be used to represent the wave magnetic field and the particle phase space density F. The phase space density is assumed to have a spatially homogeneous component called G here, and a spatially varying component that is represented by the Fourier series with the components delta F sub k. The Vlasov equation is printed in the center of the slide. If we stick the Fourier series just described into the Vlasov equation and only retain those terms that are first order, then we get the equation on the bottom. This has the form of a linear operator times delta F sub k minus another linear operator times G, so that we can write L sub k times F sub k is equal to P sub k times J. Since L sub k is a linear operator, meaning it takes derivatives of the function it operates on, it can be inverted. This results in an integral operator. And we can express delta F sub k as the product of two linear operators times G. This is the linear solution for the kth component of the Fourier series. It gives the linear response of the homogeneous phase space density to the kth component of the spatio-temporally varying waves. The total linear response can be obtained by summing over the Fourier series using the first equation on the slide. Next slide, please. The reason that the quasi-linear theory isn't linear, but rather quasi-linear, is because it allows some second-order terms. That is, the product of two first-order terms to contribute. This is seen in the center equation on the slide, where we see the product of the first-order terms due to the electromagnetic waves and the phase space density. Since the product terms inside the parentheses will depend on both space and on phi, the component of velocity in the gyrophase direction, but the ultimate solution doesn't depend on these variables, we simply average over space and phi to produce the final result. After a lot of algebra that you can review for yourself in Appendix A of the paper, we get something like the last equation on the slide, where the g-hat terms are again differential operators. The squared term in the center contains the electric field vector. The delta function enforces the well-known resonance condition, and the integral over Cartesian wave vector space is represented in cylindrical coordinates. The integral over psi, the azimuthal wave angle, can be performed because the result does not depend on the distribution of wave power with respect to psi, as one might expect since psi only controls the direction of the wave in the gyrophase direction. However, in Kennel and Engelmann's paper, the final equation actually has a dependence on psi. This appears to be a notational error that's corrected without comment in the 1971 paper. You can read more about this in Appendix A of my paper. Next slide, please. So the diffusion equation can be written in an incredibly compact form, as shown in the first equation here, where the matrix of diffusion coefficients is called the diffusion tensor. Each of the four terms in the diffusion tensor has a form like that in the second equation on the slide. Again, the delta function represents the resonance condition, and we still see the integration over k perp and k parallel. However, here I have expanded the terms for the Fourier components of the electric field vector so that you can see that only the squared quantities of the left-hand, right-hand, and parallel components of the electric field distribution contribute. This means that the diffusion coefficients are linear in the electric field wave intensities of each of these three components, and so superposition would be obeyed in these quantities. Next slide, please. In Larry Lyon's 71 paper, he shows how the cold plasma dispersion relation can be used to eliminate the individual components of the electric field, since the left and right hand circularly polarized components can be expressed in terms of the parallel electric field, leaving only 1 degree of freedom. This one remaining degree of freedom can just as easily be the wave magnetic field intensity, as shown in the bottom equation on this slide, as it can be the electric field intensity. Now note that the diffusion coefficients are linear in the wave magnetic field intensity, and so superposition also applies to the total wave magnetic field intensity. That is, if I have two distributions of wave power, I can first sum them and compute the diffusion coefficients, or I can first compute the diffusion coefficients of each distribution and then sum the result. Either way, I get the same answer, as one might expect. This is not true when one uses transformation of variables in Lyon's paper that I discuss next. Next slide, please. In the 1971 paper, Lyons argues that one may want to specify the wave power as a function of frequency and tangent of the wave normal angle, which can be directly extracted from measurements, rather than specifying the power as a function of the 3D Cartesian wave vector, which is not directly observable unless you have a large number of closely spaced satellites making simultaneous measurements of the waves. We realize here, based on previous slides, that bk squared as a function of k perp and k parallel is shorthand for specifying the distribution of power in the 3D Cartesian wave vector space. And we ask, how do I transform the distribution of wave power? The correct way to do this is to visualize, as I did on an earlier slide, an infinitesimal volume in k perp k parallel space on the left here, where psi is suppressed. The amount of wave power in that volume is bw squared. After transformation of coordinates, the total wave power doesn't change, so we still have bw squared, but the volume in frequency in x, where x is the tangent to the wave normal, is different than it is in k perp k parallel. If we multiply the distribution function in frequency in x space by the volume in that space, it must equal to the same product as in k perp k parallel space. This equality results in the correct formula to use for relating the distributions of power in these two spaces, shown in the pink box. The Jacobian of the transformation, which is physically the ratio of infinitesimally small volumes in the two coordinate systems, is used to normalize one distribution to the other. Next slide. So in Larry Lyons' later sole-authored papers in 1974, he allows the distribution function in frequency and wave normal angle to be arbitrary by letting the wave normal angle function g depend on both frequency and wave normal angle. The normalizer used here to relate the two distribution functions, though, is an integral of the Jacobian rather than just the Jacobian. Appendix C of the paper speculates that Lyons ended up in this spot by first trying to simply equate the distribution functions to each other with no normalization. That is, by just applying a coordinate transformation to the arguments of the distribution functions. But then he found that when he tried to integrate out the dependence on the wave normal angle, he didn't get the desired power spectral density b squared as a function of frequency. The normalizer, n of omega, corrects this so that when one uses the wave distribution in Cartesian wave vector space indicated by equation A3 here on the slide, the power spectral density with respect to frequency is preserved. If this is what Lyons did, it is apparently a common mistake because Roederer and Zhang, in their recent book, devote a small section of their recent book to this issue and point out that use of the Jacobian to modify the distribution is often done incorrectly. Next slide. So very quickly here, I just want to point out that Glauert and Horn's 2005 paper, and which these equations are taken from, and also J. Albert's 2005 paper, inherit this normalizing function n of omega. The rest of the terms are identical to what I showed earlier after transforming from k perp and k parallel to frequency in x. Next slide. So a concise statement of the problem is then that the correct way to relate the distribution of power in Cartesian wave vector space b sub k squared to a distribution as a function of frequency in x is listed on the top here, where there are two Jacobians that contribute, one associated with the transformation from Cartesian to cylindrical coordinates and one from cylindrical coordinates to frequency in x. However, the relationship used in Lyons and the other papers through Glauert and Horn 2005 and Albert 2005 is in the second equation here, which has an integral of the Jacobian weighted by the wave normal angle distribution. Next slide. So the first problem with the normalizer used in Lyons 71 and those later papers is that it isn't well defined when the tangent of the resonance cone angle is an endpoint of the integral. That is, when x sub rc, the tangent of the resonance cone angle, is less than x max, the endpoint of the integral. Glauert and Horn suggested limiting the integral to 0.9999 times x sub rc, but this seems arbitrary. The reason that the integral doesn't exist, if you integrate all the way up to the resonance cone, is because the index of refraction, and hence the magnitude of the k vector, goes to infinity. Others may argue that this behavior doesn't bother them because in a realistic plasma, the temperature is not zero. In a finite temperature plasma, the index of refraction is bounded, and so one can set the endpoint of the integral to be where the index of refraction reaches some large but physical value, say 300. The second problem with line 71 normalizer means that the diffusion coefficients are no longer linear in the distribution of wave power, and hence superposition doesn't apply. To make this more specific, suppose that you have a two-component distribution of wave power, like has been shown by Wen Li's work in the figure here. For lower band chorus, there are apparently two populations, one that is more parallel and one that is more oblique. If you use the Lyons normalizer and compute diffusion coefficients separately for each population and then add them together, you'll get a different answer than if you compute diffusion coefficients for the total population all at once. This problem doesn't happen if you use the Jacobian properly, since the diffusion coefficients are then linear in the distribution of the wave power. You can break out the calculation however you want. Next slide. So the impact of the correction that I'm proposing will be small if the Jacobian is constant over the range of integration in X, and X is much smaller than the X of the resonance cone. For the chorus wave model used in Glauert and Horn's 2005 paper, I plot the ratio of the two normalizers for two different normalized frequencies, 0.1225 in black and 0.5725 in red, and two different values of X max, one on the left as in the original paper, and X max equal to 5.67 on the right, as is used for many studies that are interested in oblique waves. The ratio can obviously be many orders of magnitude different than 1, but it can also be close to 1 for certain values of X. Next slide. Using the same chorus model as in the previous slide, I next plot out the pitch angle diffusion coefficient as a function of energy for very small pitch angle for the approach I suggest in red, and for Glauert and Horn in black. The blue line uses Connell and Engelmann with the notational error and an assumption that the wave power is uniform in azimuth, since that equation will give you different answers depending on what the power distribution in azimuth is. I look at three different values of plasma parameter, i.e. the ratio of the plasma frequency to the electron cyclotron frequency, which is 0.7 in the left column, 1.5 in the middle column, and 10 for the right column, and two different values of X max, one on the top row and 5.67 on the bottom row. One can see orders of magnitude difference between the approaches at a wide range of energies, but there is also relatively close agreement for broad ranges of energy. Next slide. So in summary, I've discussed three problems with the historical literature as it applies to evaluating diffusion coefficients with quasi-linear theory. One of these problems is just a notational error in Connell and Engelmann concerning the azimuthal angle that I glossed over here, but is described in Appendix A of the paper at great length. The second problem is that Connell and Engelmann assume that only one frequency can be associated with a given K vector, but for emic waves, it's not difficult to find multiple frequencies that share the same wave vector due to the close spacing of the ion cyclotron resonances. The third problem, and most significant in my opinion, is the inappropriate use of the Jacobian to transform the wave power distribution. This can result in orders of magnitude differences in the diffusion coefficients in some cases. So I hope folks are interested in looking into this. Thanks.
Thank you, Craig. So we have, there was a little bit of discussion in the chat with Solène, but we have time for questions and discussion for both of the talks. Please either use your, let me actually stop here so I can, yes, get back to normal view. Please unmute yourself or raise your hands. Let me ask a couple of very naive questions. My first naive question goes to Solène. Solène, very interesting talk, very interesting new approach of the way I understood it, developing basically new perturbation theory that takes into account some phase dependence of the phase space density or the distribution function. So could you comment on what would be the benefit of this approach relative to basically going full-blown solution of Vlasov equation that would take into account obviously non-diffusive effects and phase dependence and all of that.
Yes, thank you, Sasha. So this equation, it's done keeping in mind that we have existing models that are used operationally to model radiation belts, and that includes also local processes. So with this equation, right, is a more sophisticated description for the effects of radial transport. You can also add your typical local diffusion coefficients for the wave particle interactions at the local scale and loss terms. So it's a modification of your typical Fokker-Planck equation that can be of use for operational models. Now the question is, when is it really worth the effort? Because we expect that we have some regimes where actually is good enough to keep with the radial diffusion framework, and maybe some conditions, I am thinking storm time and active times, when somehow this is not telling the full story, and adding the extra terms are really necessary. So it's to somehow find the balance between the worlds of, we could say very simplistic description for radial diffusion and the full-blown, modeling that is not accessible. For example, to me with my laptop, I don't have the computing resources to do that. So, simple diffusion code, maybe it's a compromise between the two worlds. Thank you.
Thanks a lot. Oliver, would you like to unmute and ask your question to Craig? I can hold my question to you later.
Yeah, sure. Can you hear me?
Yes, loud and clear.
Great, thanks. Yeah, thanks both for the brilliant talks. This question's for Greg. I think it might be slide 17 or 18, but it was the slide where you were showing the differences in all the different diffusion coefficients that you calculate. My question was about your diffusion coefficients were more different to Glauert and Horn than they were to Kennel and Engelmann, I think. So maybe the next slide. Yeah, the differences are more marked between Cunningham and Glauert and Horn, and they're, less marked to Kennel and Engelmann. Is the difference with Kennel and Engelmann just due to relativistic effects, or can you just comment on that, please?
Yeah. Thanks, Oliver. Yeah, I should have been careful there. When I say Kennel and Engelmann here, I mean the relativistic version of Kennel and Engelmann. And so the differences there are due to these phase terms. So if you look at the kind of penultimate equation in Kennel and Engelmann, there's these exponential of minus psi terms. And those exponential of minus psi terms in that penultimate equation mean that the diffusion coefficients depend upon how the wave power is distributed in the azimuthal angle psi. And the reviewers actually were the ones that pointed out that, that just doesn't make any physical sense to have the power as a function of psi affect the result, because that's in the direction of the gyro phase motion of the particle. And so you can just shift everything in psi, and it really has no effect on a gyro phased average kind of, response of the particle to the waves. And so this is just evaluating Kennel and Engelmann as it is in the paper, assuming that the distribution of power is uniform in psi. But the correct way to do it is that you don't have those spurious phase terms, and the answer then becomes independent of the distribution of the wave power in psi. You get exactly the same diffusion coefficient if all the power is at psi equals 0, as you do if you distribute the power in psi uniformly in 2 pi. And it's really interesting because on the Thorne, Lyons, and Kennel paper from 71, their very first equation that they use is missing those exponential minus psi terms. And Jay pointed this out during the review process. He's like, what happened to the e to the minus I psi terms? They're there in Kennel and Engelmann. They're gone in the 71 paper, and he called it, mysterious that they just, disappeared. So Charlie Kennel was a co-author on that 71 paper, and my guess is that he realized that was a notational error, and they just eliminated those terms. But the appendix kind of goes through where those terms came from and where that notational error probably arose in that earlier paper, Kennel and Engelman paper.
Thank you very much. Yeah, cheers. Thank you.
More comments or questions in the audience? If not, I have a quick question.
Sorry.
No, please go ahead.
Let me just say that this is an ongoing discussion, and one shouldn't yet immediately go through all the 500 papers that have been based on the 2005 and 74 formulations. That's all.
Yeah, and just to tack onto that, we're doing some test particle simulations, and Jay and Jacob and Oliver and Dong Lai and I hopefully will be doing some test particle simulations soon to kind of, verify that this paper that recently got published is doing things correctly. So we'll just wait and see what those test particle simulations show.
That would certainly be very interesting. And, I just noticed that we're on top already a couple of minutes after the hour. So let's thank both speakers again, and we can continue the discussion offline. Thank you, Solène. Thank you, Greg.
Thanks for
Thank
the
you.
opportunity to talk.